We have these incredible ambitions for space. We want to send rovers to Mars and hunt for the very building blocks of life. But what if the biggest thing holding us back isn't the insane distance or the brutal environment, but, well, basically bad cell reception? Yeah. So how on earth do you solve a data problem that's literally out of this world? Let's get into it.
Okay, so meet the hero of our story, the Rosalind Franklin rover. This machine is an absolute beast, and it's carrying one of the most powerful instruments ever sent to another planet. It's called the Mars Organic Molecule Analyzer, or MOMA for short, and its whole job is to scoop up Martian soil and analyze it with unbelievable precision, all to find those chemical clues that might point to life.
And right there, that's our cosmic problem. See, MOMA is so good at its job, it generates a ridiculous amount of data. We're talking a fire hose of information. But the pipeline back to Earth? That's more like a slow, dripping faucet. It creates this huge data bottleneck where priceless scientific discoveries could get stuck millions of miles away, maybe even lost forever.
So how do you fix that? It's not like you can just build a bigger antenna or run a new cable to Mars. The only real solution is to make the rover itself smarter. I mean, what if instead of just dumbly collecting data and sending whatever it gets, we could actually teach the rover to think like a scientist right there on the ground?
The brain that could make this happen is machine learning, which is a part of the whole artificial intelligence world. Just think of it like this. It's a way to build algorithms that don't just follow a set of instructions, but can actually learn from what they see, spot important patterns, and make intelligent decisions, all without a human having to hold its hand.
And this all leads to a really game-changing idea called science autonomy. Now, this is way more than just self-driving. This is about giving the rover the ability to look at its own data and go, whoa, hang on, this is interesting, and then prioritize sending that specific crucial data home. It might even decide to run a follow-up test all by itself.
Okay, so giving the rover an AI brain sounds like the perfect answer, right? Well, there's a huge catch. A fundamental paradox that almost stopped this entire idea before it even got started.
You see, for any AI to get smart, it needs to train on just tons and tons of data. You know how an AI learns to recognize a cat? It sees millions of pictures of cats. But for our rover, where are we going to get millions of examples of Martian soil analysis before we've even gotten there to analyze it? It's a real chicken and egg problem. And that is the absolute core of the issue. MOMA isn't an off-the-shelf camera. It is a one-of-a-kind, custom-built, billion-dollar scientific instrument. There are literally only a couple of them in existence. And that means the amount of data we have to train our AI is incredibly valuable, but also incredibly small, or sparse.
So what do if you can't just go out and collect more data? Well, you get really, really clever. Researchers at NASA came up with this brilliant workaround. If you can't find more data, you make it.
The process is called data augmentation. And the whole idea is to take the little bit of precious data you already have and just create new but still realistic variations of it. It's almost like taking one perfect photograph and then creating a dozen slightly different versions, different lighting, different angles, to give the AI a much richer library to study from.
The researchers zeroed in on 4 main augmentation techniques, and each one was designed to mimic the kind of small, real-world imperfections and variations you'd totally expect from an instrument that's doing its job on Mars. They would shift the data, stretch it, tweak its intensity, and add some noise.
The shift technique, for example, it simulates this common problem called calibration drift, where the whole signal can get nudged a tiny bit to the left or the right. By showing the AI all these shifted versions, it learns to recognize the important chemical pattern no matter where it is. It's like recognizing a song, even if the key changes slightly. Then there's the stretch technique. This mimics other realistic effects. You know, if you find a high concentration of something, it can cause parts of the signal to kind of stretch out. This teaches the AI to focus on the overall shape of the data, not just the exact location of every little peak.
And maybe the most important one, they added noise. Look, a lab here on Earth is a super clean environment. Mars is not. Adding a bit of random electronic static and chemical background noise makes the AI tougher, more robust. It prepares it to find that one faint, super important signal hiding in the messy reality of another planet. So here's the bottom line. They took a small, very clean, and limited data set, and they completely transformed it into a much bigger, more diverse, and more realistic training library. This augmented data gives the AI the thousands of examples it desperately needs to actually become an effective scientist.
Now that's a brilliant idea in theory, but the real billion-dollar question is, did it actually work? It was time to send this newly educated AI to school and see what it had learned.
And the results? They were absolutely staggering. I mean, look at this. The models that were trained with this new augmented data showed this huge leap forward in what they could do. They performed way better and learned so much faster, especially when they didn't have a lot of time to train.
How much better? The model became incredibly accurate. We're talking about correctly identifying the right family of chemicals more than 95% of the time. This isn't just lucky guessing. This is the kind of reliable, trustworthy classification you absolutely need for autonomous science. The researchers even used a cool technique called Pareto frontier analysis to figure out the most efficient models. Basically, think of it as finding the sweet spot, the perfect recipe that gives you the biggest performance boost for the least amount of effort. This is so critical when you have to pick an AI that can actually run on the limited computer hardware you have on a spacecraft.
So, what does this all mean? What does a clever data trick like this actually mean for the future of space exploration? Why should you care?
Well, because this breakthrough just unlocks a whole new level of efficiency. It means our rovers can analyze things on the spot, immediately figure out what's the most exciting science, and send just that data home. They can even intelligently decide, hey, I should run that test again. We get to squeeze so much more science out of every single mission, whether it's on Mars or on future missions to places like Saturn's moon, Titan.
And as the researchers themselves put it, this isn't just about one mission. This is about laying a critical foundation for the future. It's about creating a new reality where our robotic explorers become true partners in the process of discovery.
And that leaves us with this one last, really exciting thought. We're solving this cosmic data problem not with bigger antennas, but with bigger brains. And when our robotic explorers can finally, truly start to think for themselves, making their own scientific calls millions and millions of miles from home, what in the world are they going to find?